On this slide, we get to the last of the combinations of functions. You can see here there are three different functions listed at the top. And for whatever reason, H is listed. Apologies, I'm not taking it out now. Anyway, we are looking for f compose. This little circle here is compose function. So we would say f compose g of 5 or g compose f of 5. And with these here, this is f compose g of x and g compose f of x. So essentially what needs to be done here is if you think of this 5, like when you have numbers, or even these x's, the input is 5, and here the input is x. And so what does this compose mean? This compose means that you are going to find f of g of 5. So our input for g of x is 5, which means I need to figure out what g of 5 is. And so I'm going to do that off to the side here. I'm going to figure out what is g of 5. Well, g of 5 is the same thing as saying 5 plus 3. Right, here's g of x. This x was replaced with a 5, so this x gets replaced with a 5. And that is the same thing as 8. So how does that help? Well, this g of 5, the input is 5, and if we input 5, we get back 8. So g of 5 is equivalent to saying 8. So we get to replace this g of 5 with an 8. So now we just get to figure out what is f of 8. Well, f of 8 is 8 squared, because whenever x gets replaced with something here, this x gets replaced with the same thing. And 8 squared is, let's see here, something squared, that something is 8, that is 64. All right, so there's the answer for that. Now I want to look at g compose f of 5. So we're going to do something similar here, but we will be trying to figure out what is g of f of 5. Well, I've got to figure out what f of 5 is in order to make some sense of this entire thing. So you'll notice again that I'm going to work on the inside first. So f of 5, that is f of 5 equals 5 squared, right? We just talked about f being the squaring function. Whatever your input is, you square it, that becomes your output. So this is 25. So again, f of 5 is equivalent to 25, so I'm going to replace that with 25. So now I'm trying to figure out what is g of 25. Well, that is something, whatever the input is, we add 3. The input is 25, so that means the answer here is 28. And this brings up a good point that order matters. So if you have f compose g, you get something. And if you reverse the order, g compose f, there's a pretty good chance you get something else. So what do we do with these other two? We have f compose g of x and g compose f of x. Well, similar to these exercises over here, we can just think of it like that. This is f compose g of x, and we don't know how to work with that yet, but I know x is my input, so work with me here. X is my input. That means g of x is equal to x plus 3. Well, that's all I got. I don't have a number anymore, but I know that I can still rewrite g of x as x plus 3. So what is f of x plus 3? What does that mean? Well, if the input changes, then it changes the x's everywhere. So this x plus 3 that's here will also go here, x plus 3. So how do you figure out what this is? You FOIL it out, you distribute it out, you multiply it out, however you like it, or however you like to say it, and it ends up being x squared plus 6x plus 9. Cool. So let's see this last one here. G compose f of x is the same thing as writing g of f of x. And if you don't like the way that explanation was for this one here, there's another way you can think about this. G compose f of x. Another way you can read this is f inside g. So way up here at the top, that means if I take my f function and I put it into the g function, then this x gets replaced with this function, right, x squared. So g compose f of x here, or g of f of x, or f inside g, we take this function and replace all the x's in this function. So that means this will end up equaling x squared plus 3. And we could have done that with this top example here too. I could have said g inside of f. So we would take x plus 3 and replace this x right here, which gives us x plus 3 squared. So however you like to think of it is good by me. I'm just trying to give you a couple of different ways to think of it so you know which works best for you. On this slide, some more compositions, this time just of functions. And I know it doesn't say it here, but I'm going to be going over the domains of these functions as well. So for the first function here, f compose g of x, another way to think of that is g of x inside of f. So how you can think of this is, I want to put 2x plus, has that 2x minus 3 in for this x right here. So what that looks like is that this will be equal to the square root of 2x minus 3 plus 1. Now that can be simplified, so you will want to simplify that. And that looks like square root of 2x minus 2, right? The minus 3 plus 1 combine into a minus 2. So here's the function, and that's fine and dandy. But what is the domain of this function? Well, the domain of this function is first based on the function you're putting into the other. So the domain of this function is all real numbers. Here, I don't see any square roots or denominators. So we're going to start with all real numbers. From there, we have to take a look at the ending function and see if this restricts anything that we started with. So now we're going to start with all real numbers because that's the domain of what we put in. But say, for example, I want to put in 0. 0 works here. 0 is 2 times 0 is 0 minus 3. This is negative 3. So g of 0 is negative 3. But if I take negative 3 and put it in here, negative 3 plus 1 is negative 2. You can't take the square root of a negative number. Not when we are evaluating functions. So what is the domain? Well, we just figured out it can't be 0. We have to look at the ending function. So what is the domain of the ending function here? You take the inside. You set it to be greater than or equal to 0. And when you solve for x, x is greater than or equal to 1, which looks like this for interval notation. So this is the domain for the composed function square root 2x minus 2. So similar ideas can be used for these other two functions here, g compose h of x and h compose f of x. And so again, I'll go through this, this one here, this g compose h of x, and then I'll give you a chance to work on the last one yourself. So here, g compose h of x really just means h of x is inside g of x. So that means I'm going to take this function here, 1 over x, and I'm going to put it in for x in the function g. So what that ends up looking like is 2 times 1 over x minus 3. And if that gets simplified down a little bit, it looks something like this, 2 over x. You multiply the 2 times the 1 together, minus 3. So here's the function g compose h of x. So now what is the domain of this function? Well, first we have to look at the function that we are putting into the other, or the inside function h of x. And with this, the domain just of that function, so I'm going to start at negative infinity all the way over to infinity, but this function doesn't allow x to be 0. That will give a divide by 0 in the denominator. So now with this new function over here, this might change the domain. It looks like the only thing that is happening here is there is still an x in the denominator, and x is not allowed to equal 0. There are no new restrictions on this domain. So the domain for the composed function or composite function is negative infinity to 0 and 0 to infinity. So this time, the domain did not change. It stayed what we started with the inside function. Go ahead and pause the video and try this last one. So here's the last one. This is f inside h. So I'm going to take this function and substitute it in for x here. So that gives you 1 over square root of x plus 1. You start with the domain of the inside function. And so if you set x plus 1 to be bigger than or equal to 0 and solve for x, you get this interval here. The x's have to be negative 1 or bigger. But then we have to see if this final composed function affects this domain. Since the square root is in the bottom, that means the square root cannot equal 0, which means x cannot equal negative 1. So that means we have to change this ending symbol, because this symbol allows x to equal negative 1, but then we just said x cannot equal negative 1, meaning we will have this parenthesis here instead. For this final idea on this exam review, we will be looking at the inverse graphs of functions. And you can go ahead and see that all these are functions. They all pass the vertical line test. So they're all functions, that's fine. I will graph all inverse functions in a bright green color for all 3 graphs. And I will also write the domain and range for each inverse in the bright green color. All right, so for this first one over here, we have this graph. And you're asked to find the inverse of this graph. Well, that's easier done than said. What you need to do is create a list of ordered pairs from the points that you see. So like I see this point is 0, 0, 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4, negative 3, and 9. So what you do is you'll create that list of ordered pairs. Let me get some black ink here. There we go. But you want to write down your points from left to right. So this would be negative 3, comma 9. This is negative 2, comma 4. This is negative 1, comma 1, 0, 0. 1, 1, 2, 4, and 3, 9. So what do you do with all of these? Well, the big idea with finding an inverse is that you swap x and y. So all of these first numbers are x's, all of these second numbers are y's. You just swap them. So the inverse points become 9, negative 3, 4, negative 2, 1, negative 1, 0, 0, 1, 1, 4, 2, and 9, 3. So let's get the green ink out. So what that means is we start here. Oh wait, we start here at 9, negative 3. So 9, negative 3 is right here. And 4, negative 2 is right here. So as I plot my points from top to bottom, I'm going to be connecting them. I know 1, 1 is right there. I know 1, negative 1 is right there. 0, 0 is right there. 1, 1 right there. 4, 2 right there. And 9, 3 right there. And I'm going to put those arrows on it. So there is my inverse graph. Well, how do you know that this is the inverse graph? How do you know you did it right? There's this line that goes up 45 degrees like this, and it goes backward like this. And if you tilt your head to the right a little bit so that this line is looking vertical, these two graphs create a mirror image around this line. In other words, it was reflected around that line. That equation of that line is y equals x. Even this equation tells you y becomes x, x becomes y. It just flips around this line. So let's talk about the domain and range of this particular function. The original function is here. Well, the domain starts as far left as it can go. That arrow is pointing up, but it's also pointing left. So it goes as far left as you can go, which is negative infinity in mathematics. And as you travel along, it goes forever to the right, which is positive infinity. Now, the range starts at the bottom of the graph, and we want y values here. So the lowest y value is 0, and then it goes up forever after that. So the range of the original function is 0 to infinity. With that information known, that the domain is this and the range is this, domain, recall, is the set of all x's, and I mentioned already that range starts with the lowest y value and goes to the highest y value. So the range is the set of all possible y values. Well, the big idea for inverses again is to switch x and y. So the domain of f inverse and the range of f inverse, that's what this little negative 1 here means. That is an inverse. All of the x's became y values. And all of the y values became x values. Oops, there we go. And you can tell this up on the graph with the domain starting as far left as it can go on the green graph. As far left as it goes, it starts at 0. But then it goes forever to the right. Forever to the right is positive infinity. This arrow is pointing to the right, yes, but it's also going down, and it goes down forever. So the bottom is negative infinity. As you trace upward, this arrow is also going to the right, but it goes up forever. it goes to positive infinity. So if you can find the domain and range of one graph, then you just switch them around. You have the domain and range for the other. I'll put these solutions to the other two over here, but I think you guys will get the idea. So here are the solutions to the other two graphs. You can find the nice points here. 1, 2, 3, 4, 5. On this graph, switch the x and y values, it gives you the green graph. So here's the domain and range for this particular function. Here in the pink, here in the green. And then finally with this one, there are only 3 nice points, but you can again tilt your head so that this either looks horizontal or this looks vertical, however you like to see reflections better. And you can see that the green graph is a reflection of the blue graph over this line, y equals x. So once you find the domain and range of this blue graph, here we go, you can just switch the order. The range becomes the domain of the inverse. Again, -1 means inverse. And the domain becomes the range of the inverse function.